I'm Andrei Manakov. In this talk, I want to cover the evolution of databases from pre-relational systems to modern NoSQL and distributed SQL databases. I also discuss the trade-offs we face and how to manage them. Let me tell a bit about myself. I've been working with distributed for 10 years, and right now I'm focusing on building ML infrastructure. Our team works on two major products, Mod and ShareChat, which together have over 3 million monthly active users. Before we dive into modern databases, let's take a quick look back to the first databases. These were complex structures where data was organized as nested trees and or graphs. In practice, working with them was extremely difficult. First, we had to manually traverse the entire field to get the record needed. Second, applications were tightly coupled to the data structure. Imagine just renaming a field and everything breaks. And finally, there was no separation between logical and physical layers. Applications had to know exactly where and how the data was stored, which made system fragile and inflexible. In 1970s, Code introduced something that fundamentally changed the way we work with data, the relational model. Instead of complex structures, he proposed a formal mathematical foundation based on set theory and first-order predicate logic. I'm sure many of you studied relational algebra at university. But it wasn't just a new format, it was a new philosophy. Code defined 12 principles, and what's important is that they address nearly all the key problems we just talked about on the previous slide. After Code breakthrough, we entered the true era of relational databases. The ideas he introduced were quickly implemented in real systems. Why did it work so well? Because relational databases had a clear formal foundation, set theory and logic. This means that the database could be built not on intuition, but on mathematics. SQL emerged unified standardized query language. For the first time, developers could work with data declaratively without needing to know how it was stored internally. Relational databases introduced transactional support based on the ACID principles. Is a completely fully didn't happen at all. No more half-saved orders on your shopping cart. They become a symbol of reliability and consistency. And of course, normalization played a huge role. We stopped storing the same data in 10 different places, and the data structure became clean and predictable. Scheme design was now based on the domain model, and again, I won't go into too much details here. I assume many of you have worked with the fifth normals from any university. This was the golden age of databases, and many systems are still built on those foundations today. And some of the systems are still well known, like Oracle or Fox Pro, which was developed at that time. However, in the 90s, a new era began, the era of mass internet access. Companies started building web applications, online stores, digital services. The number of users grew drastically. And with that came the dramatic increase in database load. So how did this affect databases? First, the volume of the data skyrocketed, but performance demands became critical. Users expected instant responses. No one wanted to wait while a server figured out how to join 5 enormous different tables. The key challenge is that relational databases were originally designed to run on a single server and process all data locally. But as the volume and complexity of data grew, they began to struggle. And in response, the industry began to adapt. And first of all, the relational database started to struggle under heavy load. The natural first step was the simple and intuitive vertical scaling. What does it mean? We simply upgrade to a more powerful server, add more RAM, a faster disk, a more CPU power, a more CPU cores. It makes sense. Everything stays the same. One database, one entry point. The advantages are obvious. It's simple. No need to change the architecture. The data is still stored centrally. We don't lose consistency. Transactions remain intact. And we can still use complex SQL queries, including joins. But there's a serious downside. Vertical scaling has a hard limit. You won't find a server with 1,000 cores. If your product has hundreds of thousands of users online, server just won't survive. The next logical step after vertical scaling was the logical database separation. But now we do it deliberately along domain boundaries. For example, imagine we have 3 areas that are loosely coupled: authorization, users, and revenue. Each of them has its own data, logic, and lifecycle. So we make the decisions to split them into separate databases. It's still simple. You're not dealing with distributed transactions or complex tools. It's just clearly separate domains, minimize coupling, and achieve isolation. The load is distributed right now. One user traffic spike doesn't affect the reporting system. If our service crashes, reports stay up and running. And we deliberately avoid joins between these domains, and we don't need them. Each domain is related and handled by its own system. However, there are limits. If the load on one domain suddenly increases, say, the number of users grows 10x. We'll again face a situation where a single instance can't handle it. The solution isn't about scaling infinitely. It's about extracting multiple logical workload, which we can optimize independently. At this stage, many teams and engineers came to an important realization. The fifth normal form isn't majority. You can live quite well without normalization. You can denormalize your data, and transactions aren't always necessary. Good performance for the product is more important than internal elegance or strict adherence to God's model. And what does this mean in practice? First, we let go of strict exit guarantees. It turns out that in most real-world product scenarios, full transactional integrity is overkill. For example, if a user clicks like on a post, it's not the end of the world if it gets lost due to a failure. You don't need a full transactional support for every minor action. Second, we denormalize data. In other words, we copy necessary fragments to different places. Yes, it embraces Code's principles and may feel like a step back to prehistoric time. But in return, we get faster reads, fewer joins, and better scalability. It's not just a technical decision, it's a product decision. It allows us to handle massive load and respond to user quickly. And of course, this approach has its downside. It requires careful thinking. You need a deep understanding of the user journey. You must consider the constraints where appropriate, while still ensure data consistency in the places that matter. There is still physical performance ceiling. At this point, we still rely on a single server. You can't add more than 1,000 CPU cores or several terabytes of memory. And the next common step is caching. It's another way to reduce load on the database, especially in systems where reads greatly overweight writes. How does it work? Very simple. Each application instances stores frequently used data in memory. For example, reference data, user profiles, settings, or query results. This gives a great performance. Instead of querying the database, fetch the data directly from RAM. It's fast, simple, and doesn't require a network request. It also reduces database load. But as always, there's a trade-off. First, data may become stale. If something changes in the database and the local cache doesn't know about it, the user will see an outdated version. That isn't a bug, it's part of the compromise. Second, caching doesn't scale the system itself. We still rely on the same single database. Yes, we vary the selling, but we are still bound the limits on this server. And we are not getting past those 1,000 CPU cores. And now we are approaching one of the most fundamental concepts in distributed systems, the CAP theorem. The core idea that in distributed systems you can achieve all three of the following guarantees at the same time. C. Consistency. All nodes see the same data at the same time. Availability. Every request receives a response, though it might be a bit outdated. Partition tolerance. The system keeps operating even when there is a network partition. So, as soon as a network partition happens, in real-world systems, it does happen. You are forced to pick just two of the three. That's what the famous triangle says. Pick two. Let's say you want your system to always respond and for all nodes to remain consistent. In that case, you can tolerate network partitions. As the network breaks, your system goes down. It's a classic CA model, and it's typical of traditional relational databases like Postgres or MySQL running as a single instance. And obviously, such systems guarantee strict data correctness, never return garbage or stale data, but can't survive network partitions or classifiers. And here's where things get interesting. Once you want to scale to distribute across nodes, you are forced to sacrifice either availability or consistency. CAP forces us to make deliberate architectural trade-offs. And just maybe a small fun fact, the theorem was originally proposed purely from empirical observations, without a formal proof. Everyone was quoting it or discussing it, but for a while it was just a hypothesis. But later, it was formally proven, maybe in 10 years. But CAP theorem is a great starting point, but it has one significant limitation. It only considers what happens during a network partition. But what about normal operation, when the network is stable? After all, partitions don't happen every day. And this is where a more complete model comes into play. Puzzle C. Puzzle C stands for, basically, if there is a partition, you have to choose between availability, and consistency. Also, basically, under normal conditions, you have to choose between latency and consistency. In the other word, the model says, even when your network is healthy, you are still facing a trade-off between latency and consistency. Take a look at the chart on the right. If you want low latency, you'll get faster responses, but possibly with stale or inconsistent data. If you want strict consistency, you'll need to wait. The operation has to reach all replicas, perform synchronous replication, wait for acknowledgements. Only then does the client get a response. This model gives us a more realistic picture of how distributed systems behave. It also reminds us that trade-offs aren't just for emergencies. They are the everyday reality of distributed architecture. And after all the trade-offs and network partitions, a natural question arises. So when should we actually use relational databases? And the answer is surprisingly simple, almost always, unless you are dealing with extreme load. If you're handling, for example, 1,000 requests per second, relational database is likely your best friend. You don't really need to scale it up. Maybe you just need to do logical split, maybe caching, for example. You'll get all benefits of relational data models, transactions, strong consistency, normalizations. Amazing. And best of all, you don't have to think about CAP or puzzle C. You just work out of the box. And this is more important. Even that scenario, you still need to account for possible failures, right? So like servers, crashes, disks, relational database aren't magic. And without proper redundancy, they become a single point of failure. So basically, you need to make some mirroring maybe, or basically smart strategy of backup. And obviously, you can build a scalable system using traditional relational databases. And I'll actually touch on that a bit later. So we can do it with MySQL or Polygraph without any additional extensions. But in doing it, you'll lose many of their core advantages. At that point, you're basically using a NoSQL database with a SQL interface, and scaling will be more complex to configure and maintain. And let's go on with our hacks for scaling. When a single database instance is no longer enough, especially in terms of read performance, many teams turn to replication. So what does it actually mean? You have one primary node. There's only one node that handles writes. From there, the primary automatically replicates data to read-only replicas. This gives us virtually unlimited read scalability. Need to handle more traffic, just add more replicas. Users read from the nearest replica. It's fast, local, and efficient. That's the important point. Replication introduces latency. So a write goes to the primary, then into a queue, and only after that is propagated to the replicas. Depending on the system load and whether the replication is synchronous or asynchronous, this delay can range from milliseconds to seconds. As a result, users might see stale data, especially if they write to one node and immediately read from another. And this is the AP model in CAP. We prioritize availability, but we sacrifice strict consistency. And another key point. All writes still goes for a single primary. So if the primary becomes overloaded, we hit a write throughput ceiling. The application is a great solution when your system is write heavy and write light. But it doesn't make your system fully scalable. It requires careful consideration of consistency trade-offs. Starting when we take one large table and split into many smaller ones, distributing them across different nodes. For example, you might route one group of users to one server, another group to a second server, and so on. The key point is sharding we scale not just reads, but also writes. Unlike replication, where all writes go to a single primary, now each shard handles its own partition of the user traffic. This allows us to scale horizontally, serve millions of users, and who knows, maybe even build our own version of Facebook. How you split data and how you split data depends on your specific case. The most common approach is hash-based sharding, for example, by user ID. Another option is using a lookup table that stores which shards holds which data. Some systems shard by geography, user type, data, or even business domain as well. But of course, it's not all smooth sailing. First, in this design, we prioritize consistency over availability. If a shard goes down, part of your data becomes temporarily unavailable. Second, you lose multi-shard transactions. You can't update two shards automatically using ACID semantics. This means your data model needs to be carefully designed. Analytical queries, like a simple cell count star, become much more complex to execute. And NoSQL emerges the industry response to the change of scaling databases. The industry began to look for new solution. A new class of data stores appeared designed not around strict schemas and ACID transactions, but around scalability and performance. As I said, we can make our relational database scaled using previous principles, but it will be just harder to do. The design philosophy is also different. It's query first. We begin by asking, what kind of queries will our apps run? When we design the data model specifically to make those queries as fast and efficient as possible. This is the opposite of the traditional relational approach, where we build a clean, normalized schema first and only later try to optimize queries on top of it. Additionally, those SQL systems don't necessarily use tables. They don't require SQL. The database has its own data model interface. Some work with JSON documents like MongoDB. Others use key value pairs like Redis. And as for transactions, in the classical sense, they are often missing. Some systems do support local transactions with a single entity partition, some comprehensive operation, but global ACID guarantees across nodes are the exception rather than the rule. Instead, NoSQL database focuses on simplicity, fault tolerance, and horizontal scalability. But what if we do need transactions that span across multiple nodes? Once our data is spread across multiple nodes or database, a new challenge appears. How can we ensure that all of them is a complete a set of operations together, or none of them do it all? To make this work, we use coordination protocols, for example, two-phase commit or more advanced ones like Texas or Raft, which are used in consensus-based system. But here's the thing. In real-world scenarios, distributed transactions introduce serious trade-offs. Firstly, performance. To commit a transaction, you have to wait for a response from every participant, even if just one of them is slow. Consensus is inherently slow, and in many cases, resources are locked until the second phase is complete. This means other operations might be stuck waiting. If the coordinator fails, it's exactly the wrong moment. The system might get stuck in the awkward middle state. The transaction is committed, but it's not rolled back either. This is a classic weakness of two-phase commit, for example. It's not resilient to coordinator crashes. And complexity. Distributed transactions are hard to implement. You have to think about TMLs, retries, failures, and duplicates in every single step, all use cases for all operators. So distributed transactions are possible, but have a lot of problems. That's why in most distributed systems, we try to avoid them where we can. And sometimes we need, as the need for scalability kept going, but so did the desire to keep transaction guarantees, a new class of database emerged. This class is known as distributed SQL. The core idea is simple. Take a traditional SQL database, make it distributed, but keep ACID guarantees and familiar interface. Everything works just like in PostgreSQL, only now it can scale across dozens or even hundreds of nodes. A SQL system preserves transactional consistency. You can use familiar transactions, expect state consistency, and design data models using well-known relational patterns. This makes the migration from legacy system much easier. Yes, and SQL is a query interface as well. No need to learn a new language or special API. And the system are horizontally scalable. They support automatic sharding, application, dispute transactions, architecture. They operate closely to NoSQL systems, but with a relational facade. But of course, nothing comes for free. Even with automatic sharding, you still have to keep in mind that when designing your schema. If frequently perform join across tables that live on different shards, those queries are become very slow, even though everything works. The same goes for distributed transactions. Yes, you can update multiple shards automatically, but it's going to be slower than performing the transaction inside a single node, which means query schema design is absolutely critical. And again, you still need to use a query-first approach rather than traditional domain-first approach in relational databases. From CAP theorem perspective, distributed SQL system usually prioritize consistency over availability and latency. From consistency preserved, but during network issues, part of the system may become temporarily unavailable. And now, in practice, global transactions across shards are rarely needed. Most of our workloads can be handled just defined by NoSQL databases with eventual consistency. And what about learning a new query language? To be honest, it's not really a problem for most developers, so it's a matter of days usually. And let's go to more practice. On this slide, we see how the CAP theorem applies to Redis in practice. Redis is a blazing fast in-memory key value store. It can be configured in different ways depending on your needs. In this setup, Redis runs in a clustered configuration with sharding. Each key is hashed and routed to a specific shard, enabling horizontal scaling. Give me a second. Let's look at this through the lens of CAP. Consistency is prioritized. Writes go to the primary node and the main card, which is critical for things like distributed logs, for example. Availability is sacrificed. If shard fails, Redis may refuse the operation to avoid serving inconsistent data. Partitions is supported. Redis can continue operating with the healthy part of the system. We are able to scale Redis by increasing the number of shards. In this configuration, we sacrifice availability to maintain consistency, which is important for correctness critical use cases like distributed logs, as actually mentioned before. On this slide, we see Redis in a different configuration. We still use sharding, but now each shard is replicated. Client write to the primary, but read from either primary or replicas. This boosts availability and partition tolerance. And if some nodes go down, the system stay responsive. The trade-off is consistency. Because of application lag, client may read stale data. So the setup favor high availability over strict consistency, ideal for caching or write-heavy systems where freshness isn't critical. And for contrast, here's another Redis configuration with no replication and no sharding. In this case, Redis behaves more like a traditional relational database. A single instance, all reads and writes go to one node. Now let's take a moment and talk more specifically about consistency. What you see here is the classic classification of consistency models. On the left, we have traditional relational models. These mostly describe different levels of transaction isolation. On the right, we have consistency models used in distributed systems. At the top, we see the strongest models, where updates appear instantly on all nodes. The further down you go, the weakest guarantees. Data might take time to propagate or be consistent for a while. But here is the thing. In practice, people often don't talk about consistency in such formal terms. Let's break down some of the most common consistency models used in practice. Strong consistency is the most reliable and strict model. After a write, all client immediately sees the same value. There is no delay, no uncertainty, everything is perfect in sync. Eventual consistency. This is the weakest consistency model. After a while, write, data is gradually synchronized across nodes. Eventually, everything becomes consistent, but not right away. In practice, this delay is usually just a few milliseconds, and it's more than enough for more real-world use cases. This model is typical for distributed NoSQL database like DynamoDB or Cassandra. And tunable consistency. Here you can adjust the level of consistency per request. For example, consider the write successful only if it's acknowledged by at least 2 out of 3. This approach is supported by systems like Cassandra and Solidity. It gives you the flexibility to balance performance and reliability, depending on the specific use case. Later, I want to basically show different trade-offs based on SQL different configuration of the SQL DB is a modern distributed NoSQL database inspired by Cassandra, but designed for much higher performance. One of its key features is tunable consistency at the query level. You can define how many replicas must confirm a read or write. This gives you direct control over the trade-off between speed, reliability, and consistency. In how request works, the client connects to any node, and that node becomes to be a coordinator. The coordinator figures out which nodes are responsible for the requested keys based on hashing. It then forwards the request to the appropriate replicas. For example, if replication factor equals 3, the write is sent to 3 nodes. The coordinator waits for acknowledgement based on the chosen consistency level. Once it's done, it returns the result to the client. The key point is the client is completely unaware of how data is distributed. All the complexity is handled by the coordinator. This allows CLDB to scale horizontally, improving both performance and resilience, so as you add more nodes. And there's no single point of failure. All nodes are equal. And see how a write works with consistent level equals all. The client sends a write to the coordinator. The coordinator forwards to all replicas. The write is only successful if all 3 replicas confirm the operation. If even one replica is unreachable, for example, due to a network partition, the operation is rejected. What this means? So we have a strong consistency, lower availability, and lower performance. So basically, we prioritize consistency over availability in case of any partitioning or latency in normal behavior, in normal operation level. This level all is used in critical scenarios, such as bank transfers, payment processing, or any case where data accuracy is more important than availability. In this situation, it's better to fail the operation than to risk data inconsistency. Another example, our write work is consist level 1. The client sends the write to the coordinator sends the write to all replicas, but it returns success after just one replica acknowledgement. The remaining replicas are updated asynchronously. What this means? Higher availability, even if most nodes are down, the writes and reads can still proceed. Last available to just using 33% of all nodes. Consistency is not guaranteed at all. Clients may read stale data. And maximum performance responses are returned very quickly. And this consistency level is ideal for newsfeed, ads, analytical pipelines, and etc. And how a write work with consist level equals quorum. The client sends the request to a coordinator, the coordinator forwards it to all replicas. if the write is successful once a majority of replicas confirm, many replicas update asynchronously. And that's basically a good balance with we have a good consistency, better availability than from consist level equals all, and still pretty good performance, faster than consist level equals all, but slower than consist level equals 1. So it's a balanced trade-off between speed, reliability, and consistency. Ideal for important but not mission-critical operations. And another trade-offs we have in databases. I want to talk a little bit about engines. This is a classic data structure that widely used in relational databases and even in some NoSQL databases. Many of you probably remember it from university again. So I won't go into internals. In short, all data is stored on disk, but frequently accessed data is cached in memory for better performance. Minimizing disk accesses is key for keeping the things fast. B3 optimized for reads, fewer disk lookups are needed to find a record. It's perfect for read-heavy workloads, but it's not ideal for heavy writes. With lots of inserts or updates, the B3 structure needs constant rebalancing, which can slow things down significantly because it will produce a lot of disk writes. And we have another type of database engines, which are based on LST3 or LSM3. LSM3 is designed for higher writes. All changes go first into memory and only later are flushed to disk and batches, which greatly improves performance and reduces disk wear. Or the system first checks in memory caches, raw cache, mem table, and immutable tables. If data isn't found there, it is from disk. A Bloom filter helps keep files that definitely don't contain the requested key. Bloom filter basically it's a probabilistic cache set. It's a data structure which helps you to understand whether data is exists anywhere or not. So this is ideal for write-heavy workloads, but if your system is already heavy with relatively few writes, AB3 may be better to fit. So always choose your storage engine based on workload. Write-heavy, go with LSM3. Write-heavy, choose B3. And a little more about modern trends. That's the finish of my talk. Today, many companies take popular battle-tested databases and rebuild them from the ground up using faster languages like C++ and a heavy optimized architecture. What important is, IP stays the same, the developers don't need to relearn anything, but under the hood, everything is new. No JVM, no segmentation, full CPU core utilizations. And the result is amazing. Massive performance gain, sometimes 10x or more, with the same features and interfaces developers already know. And what surprised me, usually everybody knows that we should not rewrite everything from scratch, but in practice, now we have a lot of companies which did exactly the same. They chose already existing technology, they write completely using a modern architecture, and they make a pretty nice business model. And what's the core feature of every such systems? They use thread core architecture. Take a look at this image, for example. On the left, we see a typical multi-threaded systems with shared resources. All the docs, the threads, are fighting over the same ball. There's chaos, logs, contention, CPU underutilizing. Now look at the right side. Each doc has its own ball. Each thread has its own data, its own CPU core. No contention, no logs, no racing, just pure efficiency. In this model, as I said, it's called one thread per core. Core handles its own workload, its own memory, its own responsibility. No context switching, no shared memory bottlenecks, everything stays with the CPU cache line. It's radically faster and it's perfectly fit for modern hardware. And in conclusion, I want to say that there is no perfect database, only the right one for your specific needs. Trade-off between consistent performance and scalability are intentional. Understanding these trade-offs is what enables us to design reliable efficiency and a well-justified architecture. That's all from me. Thank you. If you have any questions, I'll be happy to answer them. Feel free to reach out anytime through any of my available contacts. Bye-bye.